Today we're diving into one of the biggest shifts in computer design since the microprocessor itself. We're talking about the chiplet revolution, and believe me, it is changing literally everything from the ground up.
It kind of seems counterintuitive, right? I mean, for decades, the whole goal was to pack more and more power onto one single, gigantic, perfect piece of silicon. So why on earth is the future being intentionally broken into tiny little pieces? And this visual says it all. On the left, you've got the old school way, a traditional monolithic chip. One single, incredibly complex marvel of engineering. But on the right, that's the future. A whole team of smaller, specialized pieces all working together. Now, this isn't a step backward. It's actually a massive leap forward. But why? Why make the change?
Well, the story really starts with the wild success of Moore's Law, that relentless push to make transistors smaller and our chips bigger and way more powerful. But that incredible shrinking act has run headfirst into some very real, very hard walls.
You see, as we jammed more transistors into one space, we slammed into the power wall. These things get so dense they generate more heat than we can possibly pull away. Then you've got the memory wall. The processor is so ridiculously fast, it just sits there bored, waiting for data to arrive. But you know what? The biggest wall of all might just be the cost wall.
Just look at this graph. This is the uh-oh moment right here. Check out that bar on the far right. The cost to design a single cutting-edge 5-nanometer chip has just exploded to over $500 million. That path isn't just unsustainable, it was a dead end. It demanded a completely new way of thinking.
And that new way of thinking, it's actually best understood with a really simple analogy. Instead of trying to carve a masterpiece out of one giant block of marble, what if you could build it with high-tech Lego bricks? So let's meet the chiplet.
So what is it? Simply put, a chiplet is its own tiny specialized chip. One might be a CPU core, another one might handle graphics, and a third could be just for AI. Each one is an expert at its own job, and they're all designed to be connected with other experts inside a single package. And this completely flips the script. The old monolithic method on the left, that was an all-or-nothing bet. You'd spend $500 million, and if there was one tiny little flaw in that giant design, the whole chip could be garbage. The chiplet approach on the right, it de-risks the whole thing by letting you assemble smaller, proven, working blocks. But this new strategy isn't just about playing it safe. It unlocks some absolutely incredible advantages that make our processors better, cheaper, and a whole lot faster to develop. Okay, one of the biggest wins is in manufacturing. Think about it like this. Are you more likely to bake one perfect, giant, flawless cookie or a dozen perfect small ones? It's the same idea with silicon wafers. Smaller chiplets mean a much, much higher yield of working parts, and that directly slashes the cost. And we're not talking about small savings here. The numbers are staggering. By reusing proven chiplet designs and getting those better manufacturing yields, companies are looking at a potential 40 to 60% reduction in development costs. That is an absolute game changer. But honestly, lower cost is just the beginning. The real revolution here is the ability to mix and match components to create custom processors, perfectly tailored for any job you can imagine. This whole concept is called heterogeneous integration, and it's a huge deal. It means you can take a cutting-edge CPU from one company and combine it with a proven, less expensive memory controller from another. You're no longer locked into one single process. You can pick the absolute best and most cost-effective tool for every single job on the chip. And if you want to see what this looks like in the real world, look no further than this beast. This is Intel's Ponte Vecchio GPU. It's not one chip. It's a beautiful mosaic of 47 individual chiplets, all working together in perfect harmony to create a super processor built specifically for the crazy demands of AI and scientific computing. You just couldn't build this with a monolithic design. It'd be impossible. So you're probably wondering, how in the world do you get 47 different little chips to talk to each other as if they were one single brain? Well, this is where some truly mind-bending engineering comes into play. One of the key technologies is what you're looking at right here. This is something called EMI. The easiest way to think about it is like a tiny silicon bridge that's embedded right into the package. It creates an ultra-high-speed data highway between chiplets, letting them chat side by side with incredible bandwidth. But it's not just about connecting things side by side anymore. The real magic happens when we start going 3D. So the old way, flip chip, used these microscopic balls of metal to connect stacked chips. The new way, hybrid bonding, is way more advanced. It literally fuses the copper wiring of two chips directly together, creating a seamless vertical connection. And this graph shows you just how massive that impact is. Moving from the old way to advanced hybrid bonding isn't just a small step. It is a giant leap. We're talking about increasing the density of the connections, the number of data lanes between chips, by over 1,000 times. Seriously, imagine going from a small country road to a 1,000-lane superhighway. That's the kind of difference we're talking about. It makes the connections shorter, way faster, and far more power efficient.
So what's the big takeaway here? Okay, first, the era of building ever larger single chips is pretty much over. It hit fundamental walls of cost and physics. Second, chiplets are the elegant Lego block solution. They're smaller, specialized, and reusable. This new approach means lower costs, faster design times, and better chips. And finally, it's kicking off a whole new era of custom mix-and-match processors for really specific jobs, like AI.
And all of that leaves us with one last fascinating question. For 50 years, we've basically built our processors from a single block of stone. Now we have an infinite box of silicon Legos. So what incredible new things will we dream up and build next?